Greetings, everybody. So I want to tell you about this problem that deals with economizing a storage shed. And what I mean by that is that the storage shed needs to be a certain size. That's given to be 686 cubic feet. So that's how big it needs to be. No bigger, no smaller. But of course, the materials needed to build this have their own cost. And what I'm imagining in this one is that the roof is made of one kind of material, and then the base something different, and then the sides something different. Okay, so we're given that the material for the base is $3 per square foot. So if you can imagine a 1 by 1 square, it's $3 for every portion like that that makes up the base. Likewise, I'm given that the roof is $7 per square foot and the material for the sides is $2.50 per square foot. So there's a cost involved in building this container or this storage shed of the size that it needs to be. Okay. Now, there are lots of ways that you could make this. You could make it taller and narrower and have that amount of volume. You can make it wider and shorter. There's unlimited possibilities, but there's only one way to have this volume that minimizes the cost of materials needed to build it. Okay, so that's a summary of the problem as I understand it when I read it up there. So here's how I would solve it. So first, I think a diagram might be helpful. It did say that this storage shed has a square base. Okay, so it's, I don't know how big it is, that's yet to be determined, but it's X by X on the base. Okay, so I say X is the length of the side, any one side on the base, on the foundation. Okay, and then H is how tall any of these edges are, which tells us how tall or the height of the container. Okay, all right, and then I've written the cost of each portion of it, the roof, the base, and the four sides. Okay, now my goal here is to minimize the cost, but the constraint is that the volume has to be 686 cubic feet. Now, and this is an example of an optimization problem. We want to optimize something. Optimize will either mean maximize or minimize. In this case, I want to minimize the cost. Okay, the parameter that you want to maximize or minimize, whatever the case is called the objective function. And then that will be subject to some kind of constraint. And this is just in general. If there wasn't a constraint, what's the minimum cost? 0. Okay, so without a constraint, there's not a meaningful answer to what we're going to maximize or minimize. Okay, so there will be something that I want to maximize or minimize. That's the objective function. And then some kind of constraint that limits what we can do. All right, so in our case, that's that the volume has to be 686 cubic feet. Now, I need this cost function. Okay, if I'm going to use calculus, and I guess calculus is not the only way to do this. You could do this by trial and error, and maybe you could get the answer that way. Okay, but if I'm going to use calculus, if I'm going to show you that, I need some kind of function or formula that calculates the cost of building this. Okay, and I think the principle that's going to determine how we do that is that the total cost of any piece of this storage shed is the cost per square foot of that piece times the area of the piece. Notice how the units work out. The total cost would be in dollars. The cost per square foot is dollars over square feet, and the area is square feet. And I notice if I multiply these, the units cancel out, and I get dollars. Okay, so that works. Now, let's try to, with this principle, figure out what the cost function is going to be. So here's how I did it. I'd say, okay, this thing, this storage shed, has four sides, a roof, and a base. Okay, the area of any one side is X times H. See the X times H there? But there's four of them. Okay, so the total area of the four sides is 4XH. But they're $2.50 per square foot. So I multiply that by 250. And what you're looking at there for the four sides is their cost per square foot times the total area. Multiplying those together gives me the total cost of just the four sides. What about the roof and the base? Well, the roof and the base are each squares, and they're X by X. Okay, so the area of the roof is x squared, okay? And the area of the base is also x squared at $7 and $3 per square foot respectively, okay? So adding that all together from each piece gets me the total cost, and you're looking at it right there. From there, it'd just be a matter of simplifying. So 2.5 times 4, that's 10xh. And here I get like terms, 7 and 3 is 10x squared. And then we're done for now, okay? That's going to tell me the cost. That will calculate the cost of building this. All you need to know is what x is, the length of the square base, and h, how tall it is. And this will calculate the cost, okay? So part 2, I need some way to express this constraint. I mean, here I've written it like as a sentence. The volume is 686 cubic feet. But we'll need kind of like the cost. We'll need some kind of a function or equation. So this is a box, okay, with a square base and a height. The walls of the box meet the floor or the foundation at 90 degrees. Such a shape has a volume of length times width times height. So I could say that's x by h. Okay, so the volume of such a shape, such as this storage shed, is x squared times h, but the volume needs to be 686 cubic feet, so x squared h has to be 686. Okay, so that's part 2. So now I've got formulas basically for the cost, which I want to minimize, and the volume, which is my constraint. Okay, now part 3 would be this. That may be the cost function, but notice it's a function of 2 variables, x and h. Okay. In Calculus 1, we deal with functions of 1 variable. There is multivariable calculus, maybe you'll learn later, but for now, anything that we deal with has to have just 1 variable. So here's what I need to do. I need to use these bits of information together. I need to use the cost and the constraint to somehow reduce the constraint to 1 variable, because I'm just stuck at a dead end if the cost has 2 variables. So I can do like this. I can take my constraint for the volume, I can solve it for h, and then I can plug in that for h in the cost. It will look like this, with a little simplifying, multiplying 10 by 686, I get 6860, and canceling x over x squared to get me x, I'll get a function for the cost in terms of 1 variable, x, and it's 6860 over x plus 10x squared. Okay, now that does not tell you anything different than this cost function up here. It's just, it tells me the cost, but I only need to know one thing, and that's x, the length of any side of the base. Okay, all right. Now where do I go from here? If I want to minimize the cost, that will come down to solving c prime is 0. So of this right here, see this c of x, the cost function? If you can find the derivative of that and set it equal to 0 and solve it, then you'll have your answer, or you'll at least have an important part of your answer. Okay. Additionally, I think it'd be proper for me to say that in order to really prove that this tells me a minimum, I might also have to show that the second derivative is positive, which means the cost curve is concave up, and that critical point is at the bottom, or is a minimum. Okay, all right, but here goes. Let's take the cost function right there. Here's its derivative. Set the derivative to 0, and with a little algebra, I'll get that x is the cube root of 343, which turns out to be 7. So here's what I know. The square base is 7 by 7. That's how big it needs to be. You could build it different than that and still have the preferred volume, but 7 by 7 is going to minimize the cost of materials. Okay, what about the height? Okay, so because there are lots of things that somebody could ask you about this. They could say, what are the dimensions of it? Okay, how big is the base? How big is the height? Somebody could ask that. Somebody could say, what is the minimum cost? You know, they could ask you just about anything about this situation. But I guess the question, as I see it here, just wants to know, what are the dimensions? How big is the base? How tall is it? And so on. So what I'll do is this. I solve for x, and I know that that tells me how big the base is. The foundation of this storage shed is a 7 by 7 square. How tall it is, well, I'll have to look back in my equations. Is there an equation here that tells me h if I know x? It turns out it's this one. This one right here does that. Okay? It says h is 686 divided by whatever x is to the second power. Well, that's exactly what I need to figure out how tall this is. So h is 686 over 7 squared. Turns out to be 14. Okay? All right. So here is the finished product, I guess you could say. To have the preferred volume of 686 cubic feet, but to minimize cost at the same time, it needs to be 7 by 7 by 14. All right. Okay. Now let's do one more thing real quick. I've solved it and I can express the answer up there according to my work. I do want to emphasize something, that all my work here does is find a point on the cost curve. Okay. So there's this curve that tells me what the cost of building the storage shed is based on how big the base is. Okay. It puts the cost as a function of x. When I find the derivative of that and solve it for 0, I'm just finding some minimum point. You could imagine this, you could visualize it. If you had a way to draw the graph and find very precise points on it, then you could also answer it that way. So I want to do that just to enrich the discussion a little bit. Here's the cost curve, and I see that it's the scale is kind of inconvenient that this needs to be graphed on. It's a little bit hard to look at. But I do see that right of the y-axis, there is a spot where it dips down to a minimum. It appears to be right there. I imagine that if I could locate that point somehow, it would tell me that x is 7, just like I found on paper. But, you know, this graph would have to have the ability to track the points with some precision to do that. But I think we can. Let's zoom in a little bit. And I'll say, okay, that's the point that I was looking for right there. This point at the bottom there represents the minimum cost. The x-coordinate is whatever the base needs to be of the storage shed. So if I could locate that somehow, yep, so that appears to be at the bottom, and it says the x-coordinate is 7, the y-coordinate is 1470. Okay, so we found 7 earlier as a critical point when we solved the derivative for 0. My next question is 1470, that never showed up in my work, and that wasn't part of my answer. Do you see the 1470 right there? What's that? How does that play into this? I mentioned this in case you saw a variation of this question to ask you for different information. The 1470 is the minimum cost in dollars. Remember, what I'm looking at here is the cost function. It tells me the total cost of building the storage shed based on this number x, which is how big the base is. So if the question was a little different and it said, okay, what's the minimum cost attainable in doing this project? It would be $1,470. Okay, so that's what we found on paper here without drawing a graph at all and without needing a graph. You could look at the graph if you want to. They should be consistent with each other. At least in our class for the test, as we're learning calculus, I'll expect you to do things like this. Find functions, find derivatives, solve for 0, and interpret from there.